What about now? Can you hear me? Okay, great. Thank you. So, good morning and welcome back. So far, we have been discussing large fraction of the processing chain that I showed you at the beginning of the course, but along our route, we relied on the so-called optical remote sensing. This is what I usually do in a general course about remote sensing because it's generally easier to approach, to get into the topic starting from optical remote sensing because it is closer to human perception. Okay, so so far we have, let me step back to the first presentation and specifically to this graph which you have already seen where we distinguished the optical window and the microwave window. We said these are the only two places, spectrally speaking, where you can look down to the Earth from satellites because the atmosphere will not let you see through in other neighborhoods. So the type of data that we have, so two very different types of technology have been developed to operate here and to operate here. The wavelengths are so different that the technologies are radically different. Okay, we're talking about optics here, we're talking about lenses, we're talking about diffraction, things that are typical for optical radiation. Whereas you're talking about, we talk about antenna, high frequency electronics, and things like that in this window. Okay, so completely different technologies. There's practically no overlap. Okay, so far we have worked on this type of, on the type of data which is generated when you operate your devices here. Today we will look at the other neighborhood, which is that of microwaves, okay? And we will mostly talk about radar. Radar is not the only possible option when you work with microwaves. Let me point out that actually you can also consider so-called passive sensing in microwaves. So what does it mean, passive sensing? Passive means that the device is not designed to illuminate the target. This is quite obvious when you talk about multispectral remote sensing because you have an abundant source of radiation which is there for free, and it's the sun, so you don't even think about illuminating the scene. The same does not apply for the microwave domain. If you remember the graph that I showed you, sorry, I'm skipping here and there, but I think this is necessary to convey the general message. When we were discussing radiation, you may remember I told you we have a model for the behavior of the sun. So this is our illuminator, right? And this illuminator is very effective in the optical domain. So more or less here, you see we have high levels of power, whereas that power, that illuminating power goes down, steadily down, as we move further up in wavelength. So by the time we get to the microwave domain, the fact is we don't get much illumination anymore, okay? So in that area, we rely on the emission, not by the sun, but by the Earth itself, meaning that basically we leverage the spontaneous emission of the observed object itself to learn something about it. What can we learn? So this is not anymore talking about reflection. It's talking about emission of the observed object. So what the observed object throws out by its own initiative. Okay. Why are we interested in this type of emission rather than reflection? Remember that we're working in the microwave environment. So in microwaves, in microwave emission, if we do not illuminate the target, we observe what the target spontaneously emits. An interesting point here is that if you remember the Planck law said something like, you raise the temperature, you raise the radiation, okay? But in any case, the Planck the Planck law tells you what happens in the ideal case, but you're observing a real case, okay? So there will be a delta, there will be a displacement between what should be there and what you actually find there. What is interesting is that this displacement, this gap, tells you something about the object itself. So it's a very specific type of observation. What you're looking at is not an unknown reflection. What you're looking at is the difference between the predicted and the actual emission, okay? Because that difference is, for example, linked to, if you're observing solid land, that is linked to parameters such as soil humidity, okay? If you're looking at water bodies, at seas and oceans, that difference relates instead to salinity, to how much salt is contained per unit of water volume, etc. Okay? So these are very special types of remote sensing. I'm not going too much into them because this is stuff for specialists of the matter. It's very difficult to make this type of acquisitions. Especially it's difficult to make them very accurately, because you should take into account that when you operate in this setting, you're working with extremely weak signals. Remember the graphs that was here a couple of minutes ago? Went down, okay, on a log scale, it went definitely down. By the time you reach microwave, it's very, very, very weak. But nonetheless, you can build an instrument, a big one, that can collect every bit of it, account for it, and compare it with the ideal level, which is computed by whatever model, okay? And you look at that small, noisy difference to find this interesting result, which is, however, costly, as I said, in terms of measurement effort. So much so that generally, so this is half of Brazil. This is a part of South America. To give you an idea of the resolution, the spatial resolution with which you can get this type of data, we're talking about 25 kilometers, if I remember correctly, for 1 pixel of soil moisture estimation. It's big. It's big because you need to collect radiation on a big area in order to have a decent amount of recorded power, okay, for it not to be eaten by the system noise or other sources of disturbance. I mentioned this because this is the one I know best. It's the ESA mission, soil moisture and ocean salinity. I know of another mission from the NESA, which is called soil moisture active passive. This is also active because in order to estimate the ideal amount of radiation that you would have, one method that you use to do that is to illuminate the surface with a radar, whose reflection will give you some of the parameters that are needed to estimate the ideal amount of radiation from which you get the delta. Okay. Anyway, as I said, this is a very specific matter. I'm not going to delve too much into this. I only mention this for sake of completeness. Most of the lecture will be in the domain of microwaves, but considering active microwave sensing, namely considering what's called radar. Okay. So this will be basically the subject of the day today. Microwaves, but active. Active meaning that we do no longer rely on an external illumination, but we generate our own illumination. We're not happy with whatever spontaneous emission may be there, but we illuminate it spontaneously. We illuminate it by our own initiative. Now, in general, what we could say about radar, what it is important to point out is that radar was not born as an Earth observation instrument. Radar was actually born in a completely different context, which is basically military context for military purposes. And then when it developed, when it became public domain, it was later integrated into Earth observation. Why I'm saying this? I'm saying this because many of the conventions, many of the, let me say, much of the science that was initially developed on radar was born in the military context, and it was inherited in Earth observation. Like, for example, the term target, which is frequently used in Earth observation, basically comes from there. In Earth observation, when we say target, we do not mean that we are aiming at shooting at it, but it's just the object that we are observing. Okay. Okay. So the most widely known radar is surveillance radar. This is also another effect of the fact that radar was born and is suitable for security and for military purposes. The most widely known is surveillance radar, which is not the radar that we are going to focus on. Surveillance radar means that it means a device that is designed to keep a certain part, especially of the sky, but it can also be the earth or the land, monitored to spot anything, any anomaly that may represent a threat or anything that may require your attention, okay? But in our case, we deal with a different type of radar, which is called the Earth observation radar. In the Earth observation radar, you don't have, your goal is not that of discovering a threat or of identifying an unknown object. You know that a target is there and it's the Earth's surface. Naturally, it's there. Okay, it's no surprise. But you look down at the Earth's surface because you want to measure something of the Earth's surface. Okay, so you know that you can expect an input from the Earth. It's not a surprise. Your task is that of making the most out of this signal that comes from the Earth's surface. Okay. One thing we should note about radar remote sensing is that while discussing optical multispectral remote sensing, I mentioned multiple times that optical remote sensing data can easily be translated into images. We have seen examples even yesterday during our lecture in the afternoon, during our lab session in the afternoon. Because the way the pixels are arranged and the way the values relate with the physics of the scene that you are observing result into an easy way to switch a pack of numbers into an image. The same applies to radar. data, except the geometry is favorable, but the content, the so-called radiometry of the data set is not. So you can for sure apply the same criterion and generate an image out of radar acquisition, but that image is not as easy to understand and interpret as it used to be with optical data. Okay. So yes, in principle, you get radar images, but don't expect to be able to interpret the content of that image if you're not familiar with it. Okay, your everyday intuition, or even your expertise in optical remote sensing will have a limited impact on your capability to interpret this type of images, because the rules that lead to having a certain value for the pixel here are completely different from the rules that applied here. Okay, so it's sometimes challenging. It looks like you can understand it, but then you can't. And again, you realize you can't. And the reason lies in the fact that you're operating on completely different wavelength and with completely different physical mechanisms that are activated for doing these measurements. Okay, now let's take a walk through the landscape, to the environment around the radar. We have already discussed this distinction in surveillance and Earth observation, but some other things are not as interesting. Yeah. I mentioned that unlike for optical remote sensing, radar remote sensing illuminates the target by its own initiative. So when you're designing a radar system, you need to design a device which is capable of generating a microwave beam and direct it at the observed area. This beam can be continuous, or it can be emitted in impulses. So once in a while, you send out a flash of microwaves, and then you listen for the returning wave. In this case, you don't send out flashes, but you send out continuously the microwave. The Earth observation radar operates in an impulse mode. So radar satellite for Earth observation will generate flashes of microwave beams, okay? Not continuous, for various reasons, including the fact that this is very expensive energy-wise. So we rely on flashes rather than on continuous emission. Then, this is another novelty with respect to optical remote sensing. We didn't discuss that much, but at the beginning of the course, I said you're dealing with waves, right, with electromagnetic waves. And waves come not only with an amplitude, how strong they also come with a phase. So how is their zero placed with respect to a reference, right? This is, I think, this is a concept which is familiar to any one of you. If you have a sine wave, its phase is its placement with respect to a reference zero. Okay, something that you never consider measuring when you use an optical system. You only talk about the intensity, which is what we record. Okay, what we saw in band 2, band 3, band 4, et cetera, these were all intensity values, never phase. We don't care about the phase. And there's a physical reason because we don't care about phase in optical systems, because the phase is random. The phase of the waves emitted by the sun in the optical window is random. So there's no point in measuring it. You're just measuring a chaos. No way. In the case of radar, the story is different. you are generating the wave, you are generating an orderly wave, so how much the target changes it or messes up with it also gives you information. So you don't want to let it escape. You measure it because it's top up to the amount of information that you're collecting. This is a big change when you move from optical to microwave remote sensing, to radar remote sensing. You are interested in phase as well. Okay. Now, in Earth observation, the typical radar is an impulse radar, and it is coherent. So we use impulses, and we collect intensity and phase about the observed object. Let me give you a couple more terms that we will move on to define to the operation of the system. Radars may also be monostatic or bistatic. A monostatic radar means that the antenna, remember that we're talking about antennas now, no more lenses or no more diffraction point. We're talking about microwaves, so this is an antenna. In a monostatic radar, you have a single antenna which is switched between transmission when you're sending out the flash and reception when you're listening for the echo from the target, right? Okay, so this is the monostatic case. But you can also have a bistatic case where you have two antennas, one transmits the impulse and the other one receives the impulse. Since in the Earth observation domain, since you have a satellite, okay, and the satellite has a limited space, the most common solution by far is this one. You have one antenna sitting on the satellite, and it does both jobs, naturally. There are exceptions. There's this system by the German Space Agency, which is called Tandem-X, where they basically sent two satellites in orbit. One switches the antenna from transmission to reception in a classical way. Then a second satellite was added, which is only receiving. Because if you consider the system of the first and then the second satellite, that's a bistatic system. Okay, so while the first one does its own job and it ignores the second satellite silently listens to the backscattered field from a different viewpoint. So you have a monostatic and a bistatic system at the same time with the same illumination, which is very useful for some type of applications which we will see later today. Okay, now one more interesting difference between optical remote sensing and radar remote sensing is that the breadth, the extent of different wavelengths that can be used in the microwave domain is broader than in the optical case. Again, if you remember, the optical window ranged roughly between 0.4 to 10 microns, 10, 12 something microns, which is, I would say, well, approximately one order of magnitude, not more than that. But if you consider microwaves, then you have radars that start here and go all the way up to here. For spaceborne uses, it's a little bit more limited, but anyway, it's broad. It's 2 orders of magnitude and more, meaning that when you operate in this domain, you have a wider variety of possible reflection mechanisms that can be activated by your sensing, rather than in the optical domain. The optical domain is very narrow. It's one order of magnitude if you put everything into it, but you remember that in the optical window, we actually have two sub-windows which operate differently. Remember what they are? I ask a sudden question to keep the interest alive. What were the two sub-windows? Remember, we were looking at two very different things. One is that's correct, but that's not what I am asking you. Visible and near infrared, right? And then the other one is shortwave infrared, yeah, let's say thermal infrared. So on the one side, you have visible and near infrared, which is reflected, okay? Whereas on the other side, you have thermal infrared. So you have two operating mechanisms that are very different from each other. So the range of wavelengths that you can actually use for a given purpose is even more limited. Whereas in the case of radar, you have really a wide variability, okay? And you can leverage this variability because depending on which of these bands, these are called bands, do not confuse them. Unfortunately, this is an unlucky combination, but when we talk about bands in the optical domain, we mean the fractions of the spectrum in which we have broken down our observation. Remember, when we saw the exercise yesterday afternoon, we saw that Sentinel-2 has 13 bands. These bands are the portions of the spectrum that are sensed by the instrument, okay? In this case, in the case of radar, bands have a different meaning. Bands are fraction of the electromagnetic spectrum in which you can decide to operate the radar. Radar acquisitions are not multispectral. They generally take place on one frequency, and that's it. Okay, so you have a C-band radar. A C-band radar means that you have one frequency within C-band between 4 and 8 gigabytes. For example, for Sentinel-1 is 5.6 gigahertz. And you operate it at that frequency. And that frequency happens to be in band C. This has been, partition of the spectrum was decided several years ago, and it is still used, was decided several years ago, again, in the military domain, then it was adopted in the civilian domain, because it is convenient, because you know that when you're operating here, regardless of the exact frequency, you can expect certain properties. If you move to a different band, you can expect other properties which are different from the previous. Like, for example, typically, C is a general purpose band. Sentinel-1 operates in band C, and band C, you have a mix of all the properties that you may be interested in. Whereas, for example, if you consider X-band satellites, like the Italian Cosmo Skymed, are typically designed for very high resolution sensing, for reaching finely detailed data sets, okay, etc., etc. L-band is suitable for interferometry, etc. So it's just a matter of convenience. So let me skip all this. And, OK. Now, one important thing to point out here is we are illuminating the target. So we send out an impulse, and then we listen for the backscattered field. And the measurement sources generates different pieces of information. One thing that we can measure here, and which was not available with passive optical remote sensing, is the distance of the object that caused reflection. Since you are sending the illuminating impulse, you can also clock it and see how much time elapses between the departure of the impulse and the return of the reflected wave. So this is the distance information. We will see later that this is a very useful information, even though you're not doing surveillance. But being able to estimate the distance is very important to better understand the data. So first, information item, distance. Second, information item, intensity. This is something we're familiar with because it is shared with optical remote sensing. You obviously measure how much radiation, how much power comes back from the observed object. But then, this is less familiar. Phase, as I mentioned, phase, we take a 0, and then we measure how shifted is the wave, the returning wave, with respect to that 0. And then we also have polarization. We have to do with a traveling electrical field. Okay, another thing we can measure is the orientation of such electrical field. Why not? See, in the optical domain, we don't do this for the same reason why we don't do this. Because the orientation of the electrical field in sun-generated waves is random. So there's no point in measuring, unless you want to gamble, okay? Unless you want an engine for a gambling machine, there's no point in measuring it, okay? In this case or in the optical? In this case, yes. Yes, definitely. That's the point of doing the measurement. Yes, definitely. But based mostly on radiometric and spatial information. Radars do not generally provide any spectral information because they operate on a single band. Since your colleague raised the question, let me make this note, because it can help you also understand the rest. In the optical domain, we have discussed a lot the concept of spectral and spatial information, meaning that spectral information, you look at the behavior of the object at different wavelengths. In this case, you have no such information for various reasons. We don't have time to go deeper into them, but in this case, you operate on a single wavelength. You decide where it is placed when you design the system, and then it stays there. There's no multi-spectral acquisition. Okay? It doesn't make much sense. One of the reasons is because there's no spectral behavior here. What was the point of looking at the spectral behavior in the optical case? Remember it? Why did we measure the spectrum? Why? Let me think. Remember this. Yeah. Why this shape? Yeah, but why? Right, so part is the purpose, part is the reason. I'm interested in the reason. Why a specific type of material will give you this, and another type of material will give you this. Then your purpose is obviously to say, okay, let me identify them. But my question is, why do I find myself in this situation where I know that, why this is like this and not like anything else? Because these wavelengths, the optical wavelengths, are so short that they can activate atomic and molecular resonances, remember? So you're looking at the inner structure of the matter that you're looking at. And if you change the wavelength, you change the mechanism, and so you get a different reaction. So if you look at the different wavelengths, you will see slightly different responses, and that's revealing about the nature of the object that you're looking at. Nothing like that happens here in the microwave context, because you're moving from nanometers to centimeters. It's a completely different story. You don't look into the matter. I lost you somehow. Okay. Let's roll back. Let's stick to the fact that there's no point in radar in microwave remote sensing to go multispectral. Okay, so we limit ourselves to one single frequency, and that's it. And let's focus instead our attention on the new elements that we're bringing in, so phase and polarization and distance. The fact is that if you look at the typical configuration of a radar system, you will notice that there's a so-called master oscillator whose signal, which is like a pacemaker, which memorizes the zero that we have set by generating the impulse. And this wave is used both for sending the impulse, but also for interpreting the returning wave. So this means that when you send out your illuminating wave, you somehow keep track of the zero. And when the reflected wave comes in, you compare that reflected wave with the zero that you have memorized in time. Okay? Yeah, I know I'm on the verge of losing you. I'm trying to keep you in because all this information are relevant to understanding what you can get from radar acquisition. Okay, so I know it can be a little bit an uphill path, but believe me, it's relevant. So what you do is you send out the impulse, but then you keep track of the zero of that wave. And when the wave comes back, you compare the zero of that wave with the zero of the wave that went out. Why? Because you kept it running. You didn't switch it off. You kept it running. It's still there. And when the other wave comes back at the same frequency, you can compare them. Okay. This is very important. It's called phase measurement. Okay. Now, let's move on. So when you take the next step, something strange happens. So I said, let alone polarization. We will discuss that later. But let's focus on amplitude and phase. When you read a returning wave, you measure its amplitude. This is something we're familiar with. We did it also for the optical domain. And if we represent that piece of information into an image, it looks somehow familiar. Okay, not as much as optical, but still somehow familiar. In this case, what is this? It's a natural scene. What do you imagine it can be? Does it make sense to your eyes somehow? The picture is ugly, but it's still representative. Doesn't it look like a volcano? Maybe, yes. Yes, it does. It's the Etna volcano in southern Italy, in Sicily, acquired by an old satellite called ERS-1. And represented, this is the amplitude signal, and it is represented here. Since radar data is typically single band, it is represented visually as a grayscale image. And typically, it looks like an optical scene illuminated from one side. You see that one side of the volcano is much brighter than the opposite side. Okay, this is typical for radar data, and there's a reason for that that we will see later. But the fact is, if you consider the amplitude data or the intensity data, the image that you obtain makes sense to the human eye. If you consider the phase information instead, it doesn't make any sense to the human eye. Okay? So we set up all this device that measures the zero and then et cetera, and then compares and then sees how much is the shift, and then this is the result. It looks random. It can be considered random. Okay, so why should we bother? Why should we bother about measuring this thing that looks random? There's a reason we will see later, because there's information which is encrypted within the seemingly random pattern. Okay, so for now, you can say we have an amplitude component to the radar data, one band, so the matrix will not have multiple layers. It's going to have only one layer, or at most two layers, amplitude and phase, but not multiple layers as we have seen yesterday in the optical domain. Okay, let me give you one more example. This is one acquisition on one random place that I took from the older version of the Copernicus portal, one island next to Africa, where you can see here the so-called quick look image, where the spatial information, which is contained in the image, clearly tells you, notwithstanding, oops, this is working. This is working. Maybe, yeah, it shut off everything. Yeah. But I think we need to first check what happened, because if we just reactivate them, it may not be. This is fine. Maybe try with one. Possibly. But this is strange, because it's the same load as we. Yeah. That seems okay. Okay, so I was bringing up this example because that ugly image was too ugly. So I thought of taking a more recent example. So I took the Sentinel-1 image from an island, and I wanted to show you the intensity, it's called intensity image, and the phase image, which look a little bit more convincing in this case than the one that I showed you. Let me text Professor Gupta. Okay, let me see what I can do without images. I think I can still tell you something, even if we don't have the backup of of the projector. So we have seen that we measure amplitude and phase. What does, and the phase is seemingly random, but it actually contains encrypted information. We set it apart from the moment and we focus on amplitude. What does amplitude tell us? Well, basically, amplitude, as you may imagine, tells us the amplitude of the returning wave tells us how intensely the observed object has reflected the radiation that we sent at it. Okay, so it is a way of measuring how reflective the object is. So this is in common with optical remote sensing. You remember that optical remote sensing was about finding reflectivity, okay? So sort of an energy efficiency of the process of reflection of the waves. We have something similar here, except the reflection is intended in one direction, so it's direction specific. It depends on where you're placing your sensor, which is at the same time the illuminator and the sensor. So typically, radar acquisitions are direction specific. Optical acquisitions sometimes may be, but generally they are not. But radar acquisitions are highly direction specific, and this is something that you need to take into account when you process the radar data. The same object viewed from different directions will give different responses, right? This is something you need to live with. That's the way a radar operates. And this is one of the issues with radar acquisitions. It is highly direction dependent. It doesn't mean that you cannot see anything. As you will see, there's a lot of interesting things that you can see from a radar reflection. But still, you need to take into account that the direction has a critical impact on the measurement, and you should act accordingly. Okay, let me see. And when I say highly directional, I mean really one typical issue with surveillance radar is that you cannot. It takes time and effort to identify an object because its reflection changes a lot. Okay, in the Earth observation domain, this will most likely mean that this is one first clue. Let me put it this way. This is one first clue of the fact that in radar remote sensing data processing, you will have to rely heavily on statistical approaches. Unlike for optical data, where the process of reflection is basically stable, okay? In radar remote sensing, as we will see, there's a number of factors that tend to mess up with your measurements. We have seen one very early example, which is the phase. They tend to mess up with your measurement, which can tell you interesting things, but you need to be able to navigate through all these issues. And as I said, the typical approach is statistical. You don't rely on the single sample, because the single sample has sort of inherent randomness, which won't help you. But you need to broaden your view and look at multiple samples, multiple in space or multiple in time or multiple in direction, whatever, multiple, okay? It may be disappointing because you say, no, I want to make a single acquisition and be happy with it. Maybe you don't know, okay? So, having said that, let's go through some of the interesting points about radar. I think we can skip this. No, let me make this just this point briefly, very briefly. I said that the typical Earth observation radar is an impulse radar, meaning that you send out an impulse and then you get a reflected backscatter. And moreover, you measure distance based on the time that it takes for the backscattered field to come back. That means that you have a limited so-called range, a limited distance that you can reach before you send out the next impulse. There's the mechanism of operation of the radar puts a limit on the range of distances that you can observe, because then you cannot wait anymore. You need to send out the next impulse. Remember that you're considering a satellite which is traveling along an orbit. You cannot wait. Okay, waiting is out of question. Everything moves. So when you send an impulse, you cannot then sit there and wait for the feedback to come. You need to move on to send the next impulse for the next area, and so on and so forth, right? So there's a limited swath that you can observe with a radar system. I'm putting it in a very simple manner, but this is the basic concept. Since the satellite moves, and since you want to observe the Earth as it moves, you cannot wait for an indefinite time. You have a maximum time you can wait, so you have a maximum distance, so you have a maximum extent of Earth's surface that you can measure with each pass of the satellite. Does that make sense? Okay. This will become relevant at a later stage. Now, these are the basics of how radar operates. Now, let's move on to just a moment. No, but actually, it's 11:30. We can actually take profit of the break to allow them some time for fixing the equipment, and also let you rest from this lecture, which has been particularly intense and exciting. Okay, so we decided to take, because it's about time, so we take a break so you have time for, yeah. Okay. Okay, so thank you for bearing with me this morning. I know it looks a little bit tough, this morning, but believe me, these are useful information. I mean, if you can stay with me, I think you will benefit from it because it's interesting in the sense of being able to leverage this type of data. Okay, thank you.
या तो फिर क्या करेंगे, ऊपर का चलता है क्या इनका LS2 का, पता नहीं वहाँ पे स्विचर ही उड़ गया, पूरा ऑफ करना पड़ेगा।